Okay, if there are no questions, let me give a brief overview of what we did last time, okay?
Sure.
So last time, we were discussing the idea of vector potentials. Electromagnetic potentials. And there are two. One is a scalar potential phi. Another is a vector, three-dimensional vector potential A. But we know that in special relativity is actually, the symmetry of special relativity is the same as the symmetry of Maxwell's equation. So in special relativity, there are no three-dimensional quantities. Therefore, these four components in special relativity are combined in a four-component object called the vector potential, whose zeroth component is given by a phi, or the scalar potential, and the three-dimensional component are given by the three components of the vector potential. So in non-relativistic language, this guy is called the vector potential. But in relativistic language, this guy is called the vector potential. Okay? We are going to call this thing, all of this together as the gauge potential, okay? It's a historical name. We don't really have to delve into why it's called a gauge potential at this point. Okay. So what is the idea behind the vector potential or the gauge potential? The idea is that we can trade in as our fundamental variables the electric field and the magnetic field, so that there are 6 degrees of freedom here. We can trade those in for 4 quantities, which is the scalar potential and the vector potential, or the gauge potential. And we can do Maxwell's theory in terms of these guys instead of these guys. How are they related? Well, they're related by the following equations. The phi is defined as, well, both phi and A are defined by the minus of the gradient of phi is E, and then there is, in the definition of E, in the dynamic case, there is also a time derivative of the three-dimensional vector potential. And B is the curl of A. And due to the vector calculus identities, that the curl grad of any scalar function is 0, as well as the divergence of the curl of any vector function is 0. Using these, we can show that these definitions satisfy the Maxwell's equations, okay? Okay. Now, the thing about the gauge potential is that they are not unique. So this is a subtlety. Gauge potentials are not unique. That is, if I change phi and replace it by phi prime, where phi prime is phi minus 1 over c, the partial derivative of a scalar function with respect to time. So lambda is a scalar function. And if I change a by a prime, where A prime is the old A plus the gradient of the same scalar function lambda, then the field strengths don't change. So for example, E changes by, so E is what? E is minus gradient of phi minus 1 over C del A by del T, right? So if I now make these transformations, by the way, these transformations have a name. They're called gauge transformations. So if I make a gauge transformation, then what happens is the first guy becomes minus gradient of phi, but then it picks up this term, which is going to be 1 over C, but this minus and this minus give me a plus sign, and then I get gradient of the time derivative of lambda, and the second term becomes 1 over C, and it's going to have the same term here, but then we are adding this term, which is going to be minus 1 over C del by del T, gradient of lambda. Now, if lambda is a nice enough function, then it's, it should, the time derivative and the space derivative should commute. And therefore, we see that this term will cancel this term. And thus, we see that under a gauge transformation, E does not change. Okay? Similarly, if I take B, and B is defined to be curl of A, and if I make a gauge transformation, then this becomes curl of A plus gradient of lambda, then I get curl of A plus curl of grad of lambda. But this is, from vector calculus, we know is 0. And therefore, we see that B is also unchanged under gauge transformations, okay?
Sir, so
Yeah.
gauge potentials are not unique in a sense that if we change alpha, if we change phi and A, but the field won't change. Is that what it means? Okay.
Yeah. So gauge potentials are not unique, okay? So the comment that we want to make is that gauge potential is not unique. And classically, it's your choice whether you use gauge potentials or electromagnetic fields. Classically, gauge potentials are a luxury. But quantum mechanically, they're not. That's what we'll see. In quantum mechanics, gauge potential are the natural quantities that interact with charged particle. Okay. So let me just, in quantum mechanics, they are the natural variables, okay? Okay. Now, in last lecture, I also gave you an example. And the example was that, suppose that I took a magnetic field, a constant magnetic field along the z direction. So this is a constant, and this is the unit vector, okay? Do you know how I could create such a constant magnetic field? It's very hard to create constant magnetic field, but they tend to curve. But approximately, how can I create a more or less constant magnetic field?
Placing two magnets very close to each other.
Right.
I mean, to
Yeah. So that's we have say North Pole and we have a South Pole, and they have to be very close to each other. So because they'll be current. So, but if I zoom in here, but creating magnets artificially is a really pain. So the way that we use construct constant magnetic field is that we basically take a very long electrical wire. So they should be connected, and shape it in a form of a solenoid. And if I now send in a current, then the constant current using Ampere's law is going to create, a magnetic field around each coil, right? The magnetic field is going to be something like this, right? Sorry. I teach my best friend's daughter mathematics, so she pinged me. Unfortunately, this friend died last year. So, okay. So, what's going to happen is that you can show that when you have such a magnetic field, the magnetic field outside is going to be 0, but inside the magnetic field will be, it'll be parallel. And far away, it's going to curve around, and far away, its intensity is going to fall very, very rapidly. Okay. So effectively, the magnetic field outside will be 0, but inside will be constant and in direction. Okay. So so that's you could create a magnetic field like that using that. So now the idea is that there should be some gauge potential associated to this magnetic field, right? And so, for example, if I say I take a gauge potential, which is AX is minus BZY by 2, and AY is BZX by 2, and AZ is 0, and of course phi is also 0. Then using the curl, you can show that we get B is equals to BZ Z hat, right? It's very easy to show. But you can show that you get the same magnetic field if you take, for example, this vector potential, which is minus BZY, AY is 0, AZ is 0, and phi is 0. So it gives you this, it gives rise to the same same magnetic field. So physically, these two things are equivalent, right? And they are connected by this gauge transformation. Okay. So this will basically, if you work this out, A1 and 2 are related by this gauge transformation. Okay. Is this clear? This is just one line about it. Yeah. Okay. So for example, we could have chosen either one or 2, right? To work with. So this choice is called, so the choice of a set of gauge potentials is called a gauge choice. Okay? All right. Any questions?
No, sir.
Okay. So now that we know what gauge potentials are, now I want to talk about how charged particles couple to gauge potentials, okay?